Moving on with our 6.4 lesson on completing the square. Sometimes our perfect square binomial will not come out with nice clean answers. Like in this case, when we have x squared plus 3x plus 1 equals 5. And again, remember, we look just at this first part when we complete the square. So we're looking at x squared plus 3x plus something to make our completed square. And it's going to look like this again, remember, x plus something. Now remember, we always say this value over 2 is what we put in here. 3 divided by 2, we can't really simplify that. We have to leave it as x plus 3 halves squared. So in this case, when we have an odd numbered b value right here, we're going to get a fraction here, and that's okay. Now, to determine what number goes here, remember that it's this number squared. So we'd say 3 halves squared equals 9 fourths. So 9 fourths is what goes right here. So, solving this out then, we'd say x plus 3x plus 9 fourths. Then again, remember, we have to subtract 9 fourths, so it's like we didn't actually change our original equation. Plus 1 equals 5. This piece here, now this right here. And we can change that into our perfect square binomial to say x plus 3 halves quantity squared, still minus 9 fourths. And I'm actually going to change these into fourths so we have a common denominator. So 1 is the same as 4 fourths, and 5 is the same as 20 fourths. So now this is what our equation is starting to look like. Combining these terms, we will have x plus 3 halves squared. Combining these terms, negative 9 fourths plus 4 fourths is negative or minus 5 fourths equals 20 fourths. And we want to get it, give us some room to work here. We'll add our 5 fourths to both sides here. So we have x plus 3 halves squared equals, well, these will cancel, get rid of those, and 20 fourths plus 5 fourths will be 25 fourths. So this right here is our, we're now looking back at that, the square root value. So we have x equals square root of our m value over there minus n, so minus 3 halves. So this is starting to look a little better. Remember, we can split up any radical. We don't want to keep a radical in the denominator. We can split it up into root 25 and root 4 minus 3 halves. From here, we can solve that out and say square root of 25 is 5, square root of 4 is 2, and still minus our 3 halves. So x equals 5 halves minus 3 halves, which we can simplify even more to say then that x equals, well, 5 minus 3 is 2 halves, which again we can simplify more and just say x equals 1. Again, to check that, you would just plug our x equals 1 back into this equation. So let's try that really quick. See what it was again. X squared plus 3x plus 1 equals 5. So, oops, eraser. We'd say 1 squared plus 3, 1. I forgot it. Plus 1 equals 5. 1 squared is 1. 3 times 1 is 1. Plus 1 equals 5. 1 plus 3 plus 1 equals 5. And 5 equals 5, so that is true. So that is how you would solve when you have an odd b value. Uh-oh. Sometimes Again, normally we were working with x squared plus bx plus c. Well, sometimes we will have an a value out in front, and the a will not be 1. We can still solve by completing the square. It'll just take a little extra step here. In this case, our a value is 3. So we can divide our whole equation by 3 to get rid of that. So when we do that, that dividing by 3 is kind of distributed to each piece that we have. So we'd say that it's 3x squared over 3 plus 2x over 3 plus 1 over 3 equals 7 over 3. Now solving this out, 3x squared over 3 just leaves us with x squared plus 2/3 x plus 1/3 equals 7/3. Now from here, this is where we go right back into solving by completing the square, which we've gotten pretty good at. Remember, this piece divided by 2 is going to be our hidden piece in here. And 2/3 divided by 2 is just going to be 1/3. So that's going to be our spot there. And if we take 1/3 squared, that'll give us 1/9. So 1/9 is the piece that we are looking for in this case. So, rewriting this all, we'd say x squared plus 2/3 x plus 1/9 and minus 1/9 plus 1/3 equals 7/3. Remember, this was the part that we were trying to get into a square. That's this piece right here. And we know that this is going to be the same as this. So we have x plus 1/3 squared minus 1/9. And again, I'm going to just get common denominators here and here. Positive 1/3 is the same as plus 3/9. 7/3 is the same as 21/9. So we're getting there. It's getting closer. Simplifying this down some more. Negative 1/9 plus 3/9 is going to be 2/9 and equals 21/9. Subtract that 2/9 from both sides. So we'll be left with x plus 1/3 squared equals 19 over 9. Again, from here, we have our big M value and our little n value. So we say that x equals square root of m minus n. Oops, or should I say minus 1/3. Now, we don't want to leave a radical in the denominator, so we have to simplify this a little bit further to say x equals square root of 19 over square root of 9, still subtracting our 1/3. So then x equals square root of 19 over 3, because the square root of 9 is 3, minus 1/3. So we can either leave it like this, or we can combine it and say x equals square root of 19 minus 1 over 3. Or if you wanted to put the radical at the end, you would say x equals negative 1 plus root 19 all over 3. Any of these is acceptable. They still say the same thing. Now again, if we wanted to check whatever one we use, if we use this one, you'd have to put this whole piece in for x when you plug it back in. But that's how you would solve in that case. We've got one more example to top it all off, and this is when we have complex solutions. Now you can't look at an equation and just say instantly like, oh, I know it's going to have complex solutions. But when you carry it out, you'll find out in the end that it will. So we treat this like a normal completing the square problem, remembering that we want half of that piece, so x plus half of 2 is 1 squared, and we want this piece 1 squared equals 1. So that is the square that we're looking for. So we say x squared plus 2x plus, I want that in blue, plus 1 and minus 1. We still have our plus 3 equals 0. This is our square from here, and this equals this piece. So we say x plus 1 quantity squared minus 1 plus 3 equals 0. Combine our like terms. We have x plus 1 squared plus 2 equals 0. This is all looking pretty normal up until this point. But here, x plus 1 squared, if we subtract 2 from both sides, we get equals negative 2, which still technically looks like our x plus n squared equals m form, except for in this case our m is negative. So from here we just solve like we've normally been doing and say x equals square root of m, so square root of negative 2, minus n. And again, this is where those concepts from chapter 5 are going to come back and help us. We say that we can split this off into square root of negative 1 and square root of 2. Remember, square root of negative 1 is I. And we can't break down square root of 2, so it's I square roots of 2 minus 1. So again, you can write it either like this, or you can kind of flip it around and say x equals square root of 2 times I. Remember, you don't want it the square root over the I. It's just square root of 2 times I minus 1. Both are acceptable answers because technically I, since it's imaginary, I is a radical too, so it doesn't matter which one goes in front of the other. Some people prefer one or the other. Doesn't really matter. Either case, we have x is root 2I minus 1. So by now we should know everything there is to know about completing the squares. So if there are any questions, make sure you ask that. Otherwise, stay golden, Byron High.